Thank you for the introduction. I will try to make my presentation in time. So thank you for the nice talk by the colleagues before me and introduced a very good background about the hydrogen embrittlement. Then I will just focus on a small problem in this big hydrogen embrittlement field. It's how the hydrogen induces the transgranular to the intergranular fracture transition in nickel material. And this collaboration with my colleague, Dr. Yuding and Professor Zhiliang. Before I start, I probably can make a small kind of like the advertisement. It's our review article, very comprehensive review published in Chemical Reviews in May this year. And I suggest that at least the new PhD student entering into hydrogen embrittlement field should have a look of the paper. It's really a lot of 59 figures with 937 references. And includes all the significant work in the field. Yeah, so Xavier has showed that in nickel alloy, we found those like when hydrogen enter into the field, into the material, and we will have this fracture transition from the transgranular to the intergranular. And a lot of work previously have demonstrated that experimentally. But then the consequence is that in the early 90s, that the oil industry believed that nickel alloys are hydrogen insensitive. So to avoid hydrogen embrittlement in the steel material, they use a lot of nickel alloy as a fastener in the oil industry, especially in subsea operation. Then later it demonstrated actually the nickel alloy with time, they became also hydrogen sensitive. So how to deal with that is an issue nowadays. And according to the Norway, the state-owned oil company Equinor, that the hydrogen embrittlement is the most expensive failure they are dealing with. And they spend a lot of money every year for that. So in 2014, Equinor first, and then the International Association of the Oil and Gas Producer, they decided to bind the nickel alloy, especially 725 and 716 for any subsea fastener applications. But still now in the North Sea, there are more than hundreds those nickel-based fastener. So how the hydrogen will influence the parts property performance. And if we can deal with those, repair those parts in the environment is an issue here. So today I will first talk a little bit about this hydrogen segregation energy spectrum by the molecular simulation and how the hydrogen induced transgranular to intergranular fracture transition by molecular dynamics. Then it's the summary and perspective. As many of colleagues have shown that hydrogen embrittlement with metal material is really a multi-scale problem. So many of us focus on the continuum level or mesoscale level that when hydrogen entered, how the property is degraded. But from the root, in the molecular and atomic level, that how hydrogen will interact with the metallic atom, especially with the specific microstructural feature of the metallic material, is still questionable. So here that we focus on the hydrogen-green boundary interaction. We insert hydrogen into the polycrystalline nickel here with around 740,000 atoms. Then we will have over 4 million interstitial sites in those polycrystalline structure. Then we focus on the segregation energy distribution of the hydrogen occupy each possible trapping sites in the interstitial sites or in the green boundary defects area, and then to see how the segregation energy distribute. And here is the result. It's very clear that if we see the typical interstitial sites, tetrahedral or octahedral sites, they will have fixed segregation energy. Well, then green boundary, of course, depending on the type, depending on the structure of the green boundary, will have this kind of the Gaussian distribution of the segregation energy. What we can conclude is that most of this segregation energy in green boundary is lower than the octahedral sites. That's why when hydrogen enter into material, they prefer to stay at a green boundary region rather than those interstitial sites. If we further divide the grain boundary into the grain boundary core and the grain boundary surface, what we can see here that most of this lower energy part is the grain core, then the grain boundary surface. So that also confirms that when hydrogen even prefer to stay with the grain boundary, but enter into the grain boundary. So really inside the grain boundary. And from this segregation energy spectrum, then we can see the severe consequence we could have. That when hydrogen into the, we move from polycrystalline to the bicrystal. So then we can focus on the hydrogen interaction with individual grain boundary here. And we simulate this very high stress field area. It's around 2 times CTOD in front of the corrective. So it's a really high stress area. Then we do the uniaxial stringing test of this bicrystal material. What we can compare here without hydrogen and with the hydrogen. Of course, we see a lot of those like the hydrogen trapping in the grain boundary area here. And also, importantly, we see that it is void nucleation and growth difference. Without hydrogen, it's happened inside of the grain. Well, that with the hydrogen, it happens at exactly the grain boundary. This we have demonstrated that when hydrogen enters grain boundary, it stays inside of the grain boundary. That's why those void form and grow in the grain part. And this indication of that when hydrogen enter into material, we'll have this transgranular fracture to the intergranular fracture transition. And if we see this tensile curve, and it's very clear that when hydrogen enter the material, it induces early plasticity. So it demonstrates this help mechanism. And if we further see this hydrogen-induced fracture mode transition, a lot of us talk about that hydrogen dislocation interaction or vacancy interaction. So borrow the advantage of the molecular dynamic simulation, we can decompose the hydrogen contribution to the dislocation behavior and to the vacancy behavior. And here is the results. That if we see how the hydrogen influences the vacancy concentration and dislocation gliding volume increase, it's so obvious that it has significant influence on the vacancy behavior, but not the dislocation behavior. So that means that hydrogen play more role on the vacancy increase. And if we see the snapshot from my simulation, it's also clear that without hydrogen, when the first kind of like the dislocation emission happens, and the vacancy concentration is about 0.09%. But with the hydrogen, first that the plasticity onset is much earlier happened. If we compare this string level, and also the vacancy concentration is much higher compared to the case hydrogen-free. This further demonstrates that this hydrogen promoted the vacancy behavior, contribute pronounced to the dislocation and contribute to this transition. And of course, we can also see further that how the hydrogen concentration influences the vacancy concentration, and also the temperature influence on the vacancy behavior. Let's see here, like when we increase the hydrogen concentration, the plasticity onset, of course, changes with the hydrogen concentration. And also the vacancy increase dramatically with the hydrogen concentration increase. And this behavior become more pronounced with lower temperature. Most because that lower temperature limit the thermal vibration of individual atom in its position. And we see this at a low temperature, how the comparison of the vacancy concentration with and without hydrogen is almost 10 times higher when hydrogen come into play. So what we can do here, we run a lot of simulation with different hydrogen concentration at different temperature, and then we monitor how the vacancy concentration and how the transgranular, intergranular, or mixed mode fracture happen with the vacancy concentration to obtain this full map of the intergranular fracture of the hydrogen in nickel. And you can see here very clearly that with this hydrogen kind of like the induced intergranular fracture map changes with the grain boundary type. Different types of grain boundary, we will have this critical vacancy concentration for this transition behavior of the fracture mode. And with those, the intergranular fracture map, we can predict like at which hydrogen concentration, at what temperature, and when your material will have fully intergranular fracture. So that means more dangerous to the performance of the parts. Yeah, let's see the summary. What we can conclude from this work is that no matter which mechanism of the hydrogen embrittlement, that the damage in the nickel material is always originated from the vacancy and the void formation. And this full spectrum of this hydrogen segregation energy demonstrate this grain boundary interaction, further demonstrate this vacancy concentration contribution to the hydrogen embrittlement, and induce this intergranular fracture in the nickel material. So from this small scale simulation, what we can obtain is that if we could have this vacancy formation, nucleation, and then void growth, then it can serve as the input parameter to the mesoscale or even continuum scale, the void-based predictive framework to predict the hydrogen embrittlement behavior. And so for this mesoscale and continuum scale simulation, there will be another talk given by my colleague, Professor Haiyang Yu, tomorrow. And welcome to join his talk. So with group members who contributed to this hydrogen embrittlement work here, listed here, and I would like to thank for your attention.